Hey, I'm putting this video together just as a short tutorial video to introduce the WSEP Tier 2 R package and to go over some of the basic use cases for it. The WSEP Tier 2 stands for the Watershed Status Evaluation Protocol Tier 2 Sampling Program. The WSEP is part of the province's Tier 1 and Tier 2 monitoring programs for watershed. The Tier 1 monitoring program is more of a desktop-based risk assessment for watersheds and subbasins, whereas the Tier 2 program focuses more on field sampling and monitoring. More information about these programs can be found at the links in the sidebar here. The idea behind the WSEP Tier 2 R package is that it contains a bunch of useful functions and scripts so that land managers and stewardship groups can develop and design their own monitoring program for any watershed or subbasin of interest. The WSEP Tier 2 R package focuses primarily on connectivity, sediment inputs, and riparian health. All you really need to get going with this package is just a basic understanding of R, as well as some familiarity with a GIS platform such as QGIS or an Esri product like ArcGIS Pro. You can also run and use this package, or the entirety of the package can be run with publicly available data, methods, and open source tools. However, you're free to substitute your own private data sets if you do have them on hand. The WSEP Tier 2 R package is currently hosted on GitHub, and it can be installed from there, from within R. There's links to the GitHub page in the description block below. I'm going to run the demo with an embedded data set for the Solom River in Courtenay, BC, but you can also introduce your own stream and road layer for another watershed of interest. So the first thing we'll do to get going here is we'll install the package. So if you just jump up to the README section to the installation here, and just copy this block, and then go over to RStudio, and then we can just install the package. You'll note here that we're going to install from either remotes or GitHub, just because the package isn't hosted on CRAN yet on R. So just the conventional install.packages won't work here. So I'll just load remotes. You may need to install it or install DevTools. And then I'll go install GitHub, ESETEC, WSEP Tier 2. Then you should see something like this come up. It'll prompt you if you want to install the dependencies too. I'd recommend that you just enter 1 there and hit enter, and then it should go ahead and install the package there along with its dependencies. Yeah, you only have to do that once on your computer, but then once it's installed, we can just load the library there and see that it does indeed work. Next thing we'll do is we'll just start to make our way down through the tutorial for the Tulsum River here. I'm going to go ahead and the data for the Tulsum River is streams and roads, and that's actually embedded inside the package as an example data set. At the end, I'll show another example for a different water body where I'll make the stream and road layer from scratch in QGIS, and I'll give you an example of how you can do that. But yeah, these are just easier to just do the first demo just with a sample data set. The next big section is the stream layer. So we actually have the stream layer here for the Tulsum River, but what we want to do is we actually want to do several processing steps to it. First, we want to convert the stream layer from whatever projection it's in to a UTM projection so that its Cartesian coordinates and XY are in units of meters. And so there's a function here that can do that determines which UTM zone the data's in and then projects it to that zone. The next function is constrain streams. And the idea behind this function is I'll just look at the help menu here for it. And so it constrains the stream layer. So there's 2 arguments here, is a length remove and a length trim. And the idea behind this is we still want to sample in small small drainages too, but we don't want to include field sites that are in exceptionally small first order streams such that when we go there in the field, there's no recognizable channel or anything like that. However, small drainages are still important inputs of sediment or potential connectivity barriers there, so we still do want to include them in the sample. And so what this will do is we can specify a length of first order tributaries to be totally removed. And I'll say that's if the first order tributary is less than 500 meters, exclude it in its entirety. And I also want to trim off the first 200 meters too. So I'll go ahead and do that here. You'll note that you can adjust the length of these for whatever watershed of interest or data set that you're using. So this function here will just constrain the stream. It just takes a while, but it's actually going through all the branches and clipping them off to make them a bit smaller. The next set of processing, which we'll want to do, is we'll want to remove lentic areas, so like lakes and wetlands and other features like that. And also want to remove some alpine areas. And ultimately what we're trying to do here is we're trying to go from an original stream layer to an adjusted constrained stream layer that kind of refines our sampling domain here. So I'll get these other two functions here and I'll get ready to run them. You can actually remove the lakes and wetlands by using the edge type code that's inside the BC Freshwater Atlas. It's a feature in there. So if your stream layer originated from the BC Freshwater Atlas, then you should use this remove lentic BC Freshwater Atlas function. If you have a different stream layer that didn't come with an edge type feature, then you can either remove the lakes manually or skip this step if you need to. Next, we'll remove alpine areas. So to remove the alpine areas, again, this function works with streams that were derived from the BC Freshwater Atlas. So the BC Freshwater Atlas in the geodatabase, it actually has X, Y, and Z geometry that's embedded in it. But by Z geometry, I actually mean the elevation too. So for each of the streamline segments and each of the points, it actually has an elevation in there. So we're able to kind of leverage that in this function and choose an elevation cutoff threshold for what we consider for our watershed to be an alpine area. And yeah, so the elevation cutoff is just going to trim all the stream segments such that they don't go above that elevation. So our sampling kind of frame excludes high elevation areas. The value you should use here will vary depending on where you are, but I'd probably recommend just playing around with it a bit and just looking at it with some imagery underneath to choose an ideal value. So I'll go ahead there and I'll remove the alpine areas. And then finally, we can go ahead and take a look if we want to at what we've done there. So I'm just going to go and plot it out. Yeah, so this is optional here, but this is just to kind of do a quick throwaway plot. This STZM function here, if you haven't seen this before, this is actually just temporarily removing some of the geometry for plotting. That's just an issue with some of the base plotting here, but you can ignore this whole little section here. It's just to generate this plot to take a look at the constrained stream layer and the original stream layer. If you're not happy with it, I'd go back to one of these functions and try changing some of the values for your specific watershed, such that you get kind of the desired output that you need. Next component we'll look at is defining strata. So throughout the WSEP program, we're primarily working with stream order as a dominant strata. So the everything that's a first and second order stream will be strata 1, and everything that's order 3 and above will be called strata 2. We're just going to manually define that here, but we'll make a note that we're adding a column to our stream layer called strata, and I'm just setting it such that small streams and large streams is strata 1 and 2. The next section here is the site types A. So we're going to develop sampling sites for 3 different programs all in one. So there's a site type A that's looking at stream crossings, site type B that's road proximity too. So that looks at where there's a long stretch of road that's running parallel to a stream. That will make a sampling point in the stream based on some other parameters to look at sediment input and condition there. And then finally, there's a riparian habitat survey, which is also kind of based on stream crossings too. And then altogether, the site types get combined into a global sampling frame for each of the different programs. So if we go back to this site type A, stream crossings, we're going to just make the layer off of the stream road crossings and define a number of sampling points. So again, I'll just copy this code here and I'll run it in. So we'll use that UTM projection again on the roads just to make sure the roads are in the appropriate projection for our area and they match the streams. Then generate a stream crossing layer just as the intersection between the constrained streams and the roads. And then finally, we'll just run a grouped random sample for this first site type. And so you can just define how many sample points you want, whatever you named your strata here above, and then input the stream crossings as your data. That's our site type A. And again, there's just like a simple kind of throwaway plot here just to take a quick look at it to make sure everything looks good. And yeah, so we can see here's our site type A, stream crossings, and strata 1 and strata 2. Then we'll move on to the next sampling program, which is site types B. And this is road proximity. So what this is doing is it's sampling areas where streams and road sections are in close proximity to each other, but don't necessarily touch. And what we're doing here is we're looking at streams that are close to roads, but it might have some kind of sediment input from there, but they aren't necessarily stream crossings too. So it's good. It applies a 20-meter buffer for the strata 1 or the first and second order streams, and then a 40-meter buffer for the larger streams. Takes the intersection of the roads and the streams within this kind of buffered distance, and then removes any stream crossings just so we're not kind of conflating the sample types A with the sample types B. And then it also removes any small stream segments from that clipped buffer, and we just define that as small segments less than 50 meters long. There's a bit of a nuanced feature here that we've just been talking about, where if there are switchbacks, those are places that potentially could contribute lots of sediment to the stream too. So there's a step at the end which we'll come to, which is kind of manually reviewing this sampling frame and potentially adding in a couple switchbacks that got cut out here. Yeah, and then what this function returns is a sampling frame of sites that are in close proximity to roads, depending on the 2 strata, and returns that back as another set of sampling sites. So I'll just copy this block here, take a look at it, let it run. So yeah, we can see here's all the arguments here. So you can go in here and there's some recommended default values, but for your specific watershed, if something's not working out or doesn't look great, you can go in and change any of these distances for a better fit for whatever you're doing. So just let that run here. It's just doing a whole series of buffers, intersections, and other things like that. And again, we're setting a maximum sample or n here for each strata. So you can inflate that if you need to. The function returns points and inline segments too. So it's this actual sample points, and then it's the stream line segments themselves that are clipped in close proximity to the roads. Again, here is this kind of just another throwaway plot just to quickly look at, see what's going on and see if we're happy with the result. And so, oops. Yeah, and so we can just see here, there's our strata 1 and strata 2 sites, and our stream layer. So again, these sites aren't necessarily stream road crossings, but they're the sites in close proximity to the roads. Okay, and then finally we'll come to our site type C, or riparian component 3. This is actually an interesting one. It's working again with the stream crossings, but it's doing a grit sample for these, just to have a spatially balanced sample across the watershed, just to look at riparian influence. And all of this is just contained in this stream crossing grits function. It just takes the number of samples for your domain, the streams, and the roads. So we'll run that, and just take a look at it. You can see it didn't actually pick up any sites. Oh, there. Sorry. Yeah, so we have a kind of a spatially balanced sampling frame of stream road crossings. Right, and then one thing I like to do is use the map view function to take a look at what's going on. The map view generates a quick kind of throwaway interactive map, which can be really helpful to kind of look at things up close and inspect them too. So yeah, this is optional here, but if you need to, you can try running map view here. Yeah, and it produces, this won't work with giant data sets, but it's fine for this one. So yeah, I can look at the streams here and then toggle some of the layers on and off, and then change the base map imagery too, and just kind of go in and just make sure everything looks good. Again, we'll have a chance to adjust these sites outside of R in another GIS program, but at least here we can just rerun the functions above before we move forward with anything else. Right, and then last but not least, we'll export all our sites. So there's this convenient helper function here that takes all the outputs that were generated above and exports them all into a folder there in a format that's nice to work with and can be uploaded into other programs or field, tablet, and mobile devices there. So I'll specify an output directory, and then I'll just click export sites here, and then I can go and take a look at it. We can see here there's a big CSV with all our sites from the different types and programs, as well as like UTM zone, east and north being latitude, longitude, and so on. Kind of a shapefile representation and KML representation of it too, which can be useful to plug directly into other kind of mobile devices and Gaia GPS and things like that. You can also kind of use another program like QGIS or Google Earth or whatever there too to kind of go through and take a look at which sites to keep and exclude based on some other criteria. And yeah, so that's the tutorial for the sample data set. The next tutorial here I'll show is how to run the WSEP Tier 2 on for your own custom watershed of interest. And thanks for watching.